Okay, see, this is basically the last lecture for this course. Although I termed it continuation of the previous topic, I will actually talk a little bit on that and then talk on some special topics very briefly, whatever possible in time. So, continuing on the hydrodynamic derivative estimates, there is another formula. For example, I just wanted to mention. See, like in the textbook of Fossen, there is a well referred book now called Guidance and Control of Marine Vehicles, Ocean Vehicles, I believe. There is another set of formulas. It goes like that. This is, but here the non-dimensional is done slightly differently. Half rho L T U. Actually, here non-dimensional done is with. I will come back to that. It is minus pi T by L minus C D 0. Then Y. In fact, the added masses are normally not. These radar derivatives. A radar by LT. A radar by LT. Okay. N delta minus half y delta. See here, there is another set of estimated derivatives given. Y, of course, here remember that the non-dimensional is not L square but LT. Actually, one L has been replaced by T. Normally it was YV by half rho L square T or L cube T, etc. But here what has happened? One of the L is replaced by T. There are different non-dimensionalization parameters. Never mind. But the point is that this formula here also is same, minus pi T by L. If you look at that, exactly same as what we have done in last class based on slender body and strip theory approximation. But there is a difference. They use this CD0 term. Basically, it is a modification using this drag part, because in slender body also we actually did not take this CD0 part. Actually, it should be CL cos alpha minus CD sin alpha, etc., etc. YR dash. Another thing in this set of formula is that they use something called added mass terms corrections. To that, this terms comes in picture here. Again comes from theory. Now here this XP is what is known as a center of pressure point, and normally XP is a distance between the center of gravity and center of pressure, and this XP is approximately, let me write it down on this so that there is no ambiguity. Center of pressure, this is approximately xg plus minus 0.1 L. Okay. Then there are other estimates is given. Xu dot is approximately minus 0.05 m to minus 0.10 m, that is 5 to 10% of the mass. Yv dot is approximately minus 70% to 100% of mass. Yr0, Nv dot 0, Nr dot equal to minus 0.01 Iz to 0.1 Iz. Of course, this is a wide variability, sorry, let me write it on, minus 0.01 to 0.1 of rigid body inertia. Essentially, that is what it says. Anyhow, what you will, okay, this is another set of formula. Once again, you will notice the basic form of them remains T by L, but there some more corrections are there. That is another form. And here of course I have also given this YD. It is based on same, in fact it is based on the same formula, AD by L by T. If you look at that, it is same low aspect ratio, assuming the lift produced is given by that, you know, pi by 2a. Okay. Then just one I will give you another formula by n there is the name of the author. It gives you, just to show, pi by 2 x1 plus 0.8 y dash I have to write fast, x n minus n r dot x1 is T by L, x there is also same, and yeah, T by L square into 1 plus 0.5 CB TB, and y is B T by L square. What I am saying, you know, is that again, see, I wrote very quickly. You can always look back at that from any book, but the main point I want to tell here, you know, in this formulas is that there is no uniform formula. Okay, theory tells us, based on many approximation, that these quantities are in proportion to T by L. Reality of course shows that it will be not only T by L, because then there is no sensitivity on geometric parameters. So then people started collecting data, making a formula based on regression. When you talk about theoretical determination of maneuvering, it is all based on mostly regression type data. You know, most of the companies who are doing it have proprietary nature data. So you don't know what is there, what formula they are using probably. But there is another set of formula. There are more sets there. The important point is that even here there is T by L square is the important parameter. It is T by L square into some corrections based on B by T, B by L, CB, etc., etc. Okay. See, so there is no end of it. I just want to tell before I close this this part, because I want to discuss some special topics, is like this. There was a famous case of a tanker called S.O. Osaka. Okay, is a tanker, and in California Bay at one time extensive field scale test of this tanker was carried out. I think it, don't remember the time, but quite some time back, maybe 60s, maybe 70s, something like that. As a part of a study, many organizations were told that you come up with theoretical estimate of coefficients and the trajectory, simulated trajectory. Okay. So there are 17 people who participated. Now I like to tell you the kind of data that the people brought in, just 2 or 3 examples, and the model. Remember, the data is kind of a model. If you use nonlinear model of type 1, you have corresponding data. But if you look at the data of, say, some of them, say YV dot, I just give an example, is multiplied with 10 to the minus 6, this particular one, or minus 5 maybe. Anyhow, never mind this, minus 6 or minus 5, minus 6 I think. Organization, say 1, like this is organizations, it varies from 990 to 2006-10. Okay, there is only one quantity, but some other parameters. Let me look at this YR. It varies between, in this case, minus 233 to, well, plus 14, 13. What I am okay. This is kind very wide variability. Now look at the forces. I want to tell you this force part also because that's important to understand. See, these are the kind of variability that the people have got. Now never mind YV, YR, because the more important part is to look at these forces. See, R versus, for example, Y. So the if I were to look some kind of approximate scale, this is 0.2, like minus 1.0, just to give you some idea. 1600. Again, you have to multiply them all with this thing. So this scatter become like that, almost going at this point to say 2100 type, coming all the way to here. Maybe this is only for 200. You know what I am saying? See, there are all these people's data light in between like that. Look at that. What does it tell me? Such a wide variability in these coefficients. Just see the scatter. Another one, if I were to take n, this n part, I mean, I just without writing, I am trying to show this n part against r dash, n dash. Here the result varies from like that all the way to like this, all this, you know, in between. So you know why I have a purpose of telling you this. The purpose is that, however, now let me also tell you that, however, when the trajectories are made, the trajectory may differ not that much as you might think, not as this much, because in the trajectory so many forces come in together, so many other things interplay, but individual derivatives differ. So therefore, when somebody tells you, you know, like in real life, that okay, I got this derivative so much, please understand this business of derivatives is a representation of forces, and there can be very wide variability. So it is still, in my opinion, a lot of developed knowledge necessary, not just formulas. You just cannot do it. I mean, I always show this example. Of course, it's quite old, but the only reason is to show that organization, that if you can all read this paper, it's there in the SNAMI proceeding, you know, transactions 1993, I believe, very interesting paper. It shows these results and the scatter of the in model, in coefficient values, in force, in everything. But the final result of trajectory is not that bad. And I'll just briefly mention how you can actually get a trajectory simulation, you know, very quickly. So see what happens. This has to be kept in mind when you are talking of doing a design. You know, when you have a, you know, derivative from formula number 1. Remember, if you use formula number 2, you might have different set of derivatives. Derivatives is something that only a characteristic. In my opinion, my suggestion is that you shouldn't look at the derivative per se. You should look at the force characteristic more and the modeling of that. Get rough idea. There is nothing sacrosanct on the derivative values, but it is important. Otherwise, how would you study? So you must keep in mind. This is the reason why, you know, like somebody asked the question, why we don't have this, you know, like exercises, problems. The problem of problems are that if I were to give a problem based on coefficient values, then you can just plug in the formula, you get some result. But the knowledge of maneuvering comes not in the numbers, but in that, but more understanding the kind of physics, the flow of physics, whether the force should be more, less, how much, the number that you estimated, is it right order, all these parts, which comes slowly. You just cannot do it overnight. That's why giving a problem, you can just plug in A, B, C, etc., and then you give a conclusion. You know, and you may, supposing A, B, C was very wrong, but as we show, the conclusion will be completely opposite. Okay. Anyhow, so this you keep that in mind. Okay. Now briefly, let me talk about something called this say trajectory. Okay. Having said that, let's talk of trajectory simulation. Okay. How do you normally do trajectory simulation? Because what will happen is that after you have got these coefficients, you need to do a trajectory simulation, right? Now your thing is that, see here, what we do in a trajectory, this ship is going like that. I want to find out this is my x and y. I want to find out is x location so of g, y location of g, and of course is orientation, that is phi, that is psi. So, I am looking at this tree. I am looking at the position with respect to a global coordinate system. Then I am looking at its psi, that is the heading angle. Now, I have written the equation of motion with respect to the body system, remember. So, according to that, what I wrote, see, I have a body system here. So, according to body system, I have this was x, this is y, this is u, this is v. So, what I have got, you know, if you remember, I have an equation where something into u dot plus something into well r dot plus something into u plus something into r, etc., plus something into delta, that is radar angle is 0. This is how the equation look like, right. In other words, I can cast this to be something into acceleration u dot v dot r dot as function of u v r delta. I can cast it this way. No, an example I could have given you quickly if I were to give. Where is this? Just 1 second. Let me quickly give an. Yeah, x. See here. Say y. I had, for example, m v dot plus u psi dot equal to y. This is equal to y v v plus y r r plus y v dot plus y r dot r dot. Okay. What I can do? See, I can bring this v dot r dot this way. So, I can say it is y m v dot minus y v dot minus y r dot r dot. Now, actually, this is r, this is u r equal to y v v plus y r r. See, this has been brought this side, this has been brought this side, minus m u r. Of course, I have to have also radar plus y delta delta. That is a radar angle, no? This hull plus y radar. So, what I end up getting is, you see, m minus y v dot minus y r dot equal to this. All acceleration terms are there. So, this full thing can be written, of course, as this side can be written all as function of u v r delta. Okay. So, it is a first order linear differential equation, simple. So, how you can find out u? Very simple. It is something like I have an equation like v dot equal to some function of u v, etc. So, I will estimate simply say t plus delta t using a numerical thing is v of t plus, basically what I will write it this way, you know, this, let me write it this way. This one I estimate as v t plus delta t minus v of t by delta t equal to these values at time t. So, therefore, v at t plus delta t becomes delta t into f at t plus v at t. What I am trying to say, you know, there is no point going through this, but basically you are using a simple linear, a simple numerical integration of this equation, because I can write this is integration of that in, because what I have got an expression is a vector velocity equal to a function of v r, etc. So, therefore, v is given by integration of v dot dt, and this integration I do numerically. But this will give you u and v and psi, but what about x? Remember, I need to find out x, I need to find out x y. So the next step would be very simple, because I also write this coordinate system. I know that I had this expression written down here just now. Just 1 second. X g dot equal to u cos psi minus v sin psi, and y g dot equal to u plus v cos psi. So same thing. So once I determine u v, then I can go to this to find out x g and y g. Exactly here, what you find here, dxg by dt is a function of u v and psi, dyg by dt. So what you do, I have found out now u and v and psi. So therefore now I apply to that and find out xg at t plus delta. That means what I am saying, that two short things. See, why have a set of equation looks like that, dv by dt equal to function of u v r delta. Then I have got dxg by dt function of u v psi. So I progressively integrate this twice to get this. It's very simple, that's how we do it. So I just want to show you that nowadays in many of this software like MATLAB and here and there, etc., many of this it's all embedded. You give a differential equation form. It's after all these are all differential equation. Dx by dt is function of this, dy by dt is function of this. It directly integrates it. Simulink and all that, it does it all the time. So really there is nothing much, but it is being done. What is important, of course, that you have to fit this correct values here. These will be all function of hydrodynamic derivatives. Other derivatives, you will start with the t0. For example, the initiation is that at t0 my delta is given some small angle. You have just given a small angle. We have to also understand that in the equation of motion, I have to, for surge equation, I have to also have thrust and resistance to be modeled properly, etc., etc. Additional things to be modeled properly. So when you do that, we can end up getting a trajectory simulation. Okay, it's very simple. Okay, so this is only just very briefly, mentioning. I believe that you will only learn this when you actually do it, and when you do it, you find it trivial. It's very easily doable. The other thing I will want to talk about is automatic steering control. See, nowadays almost all ships would have an autocontroller in place. Okay. Now your idea is to go on a straight line mostly. Now there are all these winds and waves and all coming, trying to deviate it. So what you have to do is to keep on giving this delta r as a function of time continuously, so that it maintains a certain psi. See, you are heading along this line, say this psi equal to, say just for example, say 160 degree with respect to some reference. Normally they will all measure with respect to true north, like is a 45 degrees, etc., etc. You want to go that, you are going to Andaman's exact straight line. Now of course continuously there is a deviation, and suppose a ship is actually unstable, then it will continuously try to deviate. So you need to continuously control this dr. So what you do, I need to have a controller where I have to give it this dr as a function of t automatically to make sure the heading is 0. What of course is done is that a feedback loop. No, there is a sensor that will measure what is the exact psi t with respect to what is psi t given. So I can call this to be psi error. Depending on the psi error, it will get fed back to this activator. It will automatically control the rudder. Supposing it is going on this side, then rudder will try to minimize on the other side. So you can have a very simple controller. If I just want to mention, it will obviously function of this error. So you can have something like K1 psi error. With the K1 can be some tuning factor, you can choose it. In other words, supposing it is going on, say, like right hand side, you turn the radar to make it 0. But this is actually a very simple kind of concept I mentioned, but normally this never works. So what happens, you have to actually add a term called this. This is kind of a, when k1, k2 are what is called, you can say the gain functions or some coefficients. Are you understanding what I am saying here? See that when I have a ship moving in a desired direction, I want to make it go in a desired direction. I want to head straight. I have no control on the environmental disturbance that is coming. Large waves are coming, winds are coming, etc., etc. So there is always a tendency for my ship to be deviating from the route. Now, I cannot, if you go to a boat builder, he is continuously correcting this radar, right, by hand, like you would be continuously correcting in a cycle trying to make a direction. But here, of course, nowadays the concept is more auto controller. You automatically set the controller so that it automatically keep on. In fact, I have seen myself on a ship, the radar continuously turns small. So, but the question is that then I must have a signal to the radar how much it should turn to correct the error. Obviously, I have to correct the error, so I have to turn it. And so this turn should be proportional to the error. That is one thing. Okay. So I can always, this I can determine from simulation. This I can determine from many control algorithm. As control system has now become very sophisticated. This is what I showed here. That if I just kept that, normally what would happen? If I just keep that, I'll show it to you. Normally what would happen? Suppose I want to go to this heading angle. This is my heading angle, say desired. Okay, I have gone to somewhere, say at some instant my heading is somewhere here. This is my desired trajectory, my heading is there. So when I give that, it try to overshoot, and then I correct it, it overshoot, then try to, so basically it tends to have a like that, because what would happen, see here, let's say I am having an error of plus 2 degree. So immediately I give a radar on the other side. So the radar make it go on the other side. But then by the time I come here, I want to turn it, but it overshot somewhere here. Then again I turn it. So it tends to have some kind of a behavior. So what normally people do, that you have to add another term called like this. Another, you also want to make sure psi dot error is 0. Remember, you don't want to. Another purpose to make sure psi dot, the d psi by dt, that is the rate of the error, is 0, because naturally there should not be no velocity, because you see this, the rate at which it is overshooting is psi dot, the rate at which, because this is my psi curve with t. So you want to make it 0. So then one actually adds one more term like this. So this is what is called a typical PD controller. This is known as a proportional term. This is known as a derivative term. This very, now some people can also have an integral term in a PID controller, that is going to be something like k3 into psi dt. That is integral sense the error should be 0. But I am not putting that. This is a typical PID, actually PD controller. Why I mention this is because automatic control of shape is now, or auto controller is almost a universally applied phenomena to all ships. They don't use this, they may use much more sophisticated control system than just the PD controller or PID controller, because in PID controller the problem is that one has to decide these tuning factors, and there is no unique solution, you have to optimize it. It's a question of how you approach that. An example is that in this case you could approach this way, another controller follows, it goes much nicer, another person goes like that. It depends on which one you want to choose, etc., etc. But this is the basic concept regarding controlling heading. There are similar controller in submerged body for depth, etc., which is more important, for depth control. Okay. So this is it. Is now finally I actually now, in fact, that I brought this topic of depth control. I want to just mention briefly, very briefly, and that is very interesting. You will find some typical aspects of a submarine control, a submarine behavior, a submerged body behavior. Okay. as I said, I will because this is very interesting, you know, and this I will you should pay little attention to this. Let me bring this. Where is this diagram? Yeah, okay. I love to my own writings here. See, how do I put that? We have talked all this while, and this last 20 minutes of this class I want to talk about these two very interesting phenomena which is contrary to your intuitive thinking for a submarine behavior. Take a submerged body. There is also fin here. Now, in submarine, you know, there are 2 points that is extremely important. Okay. There is a point called neutral point. Okay. This is my CG, and this distance, let me first tell you this, is given by mw by zw. This is actually similar to nv by yv in the case of, because here we are talking of, you know, like this is my z direction, remember, and up is my, because x y, so this is my plus m direction, okay, and plus theta pitching. This is actually x z plane, x z plane. This point is called neutral. Now the most important thing is this is a critical point. This point, this distance from neutral point is given by mg bg divided by vz w, like that. Okay. This is okay. V into z, actually v into zw we can call w into, wait now, actually I will not, I'll call it not that way, I'm going to call this as, I'll call it like that. Okay. No, sorry. See, let me put it this way. Okay, now we are in a point to discuss. See, there is a submarine here. Okay, there is a center of gravity somewhere here. There is a point called neutral point, which is same as what we said neutral point in for a ship. The distance of that neutral point from here is mw by zw. There are the two coefficients. Okay. What is the neutral point? Neutral point is the point where if you apply a force here, it will change depth but not trim angle. If you actually apply a force here, that means suppose here, I will come back to this here, that supposing I have here a you know, like control plane. Suppose I have a control plane here. If I apply the control plane up and down, it will change depth but not theta, so it will just go up and down like that. Okay. So, if I were to put some kind of a fin here at this neutral point, a fin, some kind of a fin, what would happen? It will simply go up and down, but not change stream angle. Now, critical point is a point which is defined to be a point where if I apply a force, then it will change the stream angle, but not depth. Okay. So, it turns out, see what happens now here is the question. This point is located at a distance of mg bg by zww. Actually, zww, in fact, here this w is uw dash, you can call it. So, the point is that, see, basically this bottom, this bottom is connected to the forward speed. In fact, actually we can, yeah, okay, this is uw dash. Okay. Now, the question is that, see, as you go higher speed, see what is bg? Bg is the metacentric height for a submarine, center of buoyancy to center of gravity. You know, B will be somewhere here, Cg is somewhere here, this is say Cb and Cg is this. As you go high speed, u becomes larger, this becomes smaller. So, therefore, this point shifts forward. But when you got a low speed, what happen? This Cp keeps going aft. Now is the interesting point. See here, supposing I have a stern plane located here. Okay, what would happen? Suppose my aft plane, the one that I use for changing depth, is located at this point. What would happen? If I were to give a stern plane angle, I would change the trim angle, but I am not going to change depth. But my purpose of stern plane angle is to change depth. Remember, what do I do with the stern plane? This is what is called stern plane angle. Okay, there is the rudder is here for turning in horizontal direction. You can say turning in vertical direction is basically your aft or stern plane. In a typical submarine, there are two planes. You know, this is called stern plane. This is called a bow plane. Okay. Now, the point is that, see, if this is aft of Cp, okay, so when I turn it to go down, what would happen? This applied force here, at this point there is no change in depth, but if you make it aft, one can show that if this point is aft of this, then there is a change in depth in one direction, goes down. But if this becomes forward of Cp, then it goes up. I will show you this diagrams, this critical point diagram here in very nicely. See here. Here I give delta S like that, stern plane, my Cp is here, Cg is here and neutral point is here. Then this will cause the vehicle to turn. But if Cp is here, this would cause vehicle to go up. Now, you see this the point of interest here. Okay, this is just realize this again. My neutral point is fixed. Okay, given submarine, neutral point is fixed because neutral point distance we have seen that is mw by zw. But we have seen that this distance is actually given by it is inversely proportional to u square. Okay. So, naturally what is happening at higher speed, my Cp is somewhere here, but as I go to lower speed, my Cp actually keeps shifting back. Now, there is what is happening at Cp itself, if as I mentioned in earlier one, if I keep a stern plane and if I turn it, it is essentially not changing depth, only angle. Remember what happened. I will come to that again later. Now, you see here, if I were to keep it, so at high speed, when I turn it, say this way I turn it, stern plane, it is called dive, like you are giving turn, so naturally force comes this side and therefore the ship turns downwards. Okay. But now, let us say you are your helmsman and your dive depth is supposed to be like bringing the stern plane down is dive, but at lower speed, now you are going at 3 knots, CP has turned out to be here. Now, I gave a dive down, vehicle begin to move up. This is what is called a reversal phenomenon, very interesting phenomenon, reversal phenomenon. That means you cannot tell for stern plane that if I give it down, it will always go down at very low speed. That means what is happening, see there is a speed at which the CP has just exceeded this. So, at the point when CP has just come to the sea, as long as CP is in front of that at high speed, as I give dive, it will just dive down. Now, I am slowing down, okay, it is still diving down, but at lower rate. Now, I come to a point where I basically give an angle, but it does not dive, it is simply giving a trim angle. That is what we said, no, that is the characteristic of the point, it is simply changing the trim angle, but not diving anymore. Now, I go further slow, the point go beyond that. Now, I give a dive angle and go opposite side, goes up. So, what is happening is that if you give delta S versus like this speed, critical speed will basically come down to be like that. Typically like a critical speed, let me tell you this part, just 1 second, I need to tell you this. X by no, this is V and this is actually the location of the CP location. As the speed goes up, this distance keeps shifting up. So, why it is important is that in any submarine, typically it turns out that there is a critical speed, it is around 3 to 4 knots, and therefore, you should not go beyond that, because at that point things become very awkward. That is one thing. Second thing is that I tell you this other thing connected to this. Before that, what about the bow plane? Bow plane is either here or here. Now, typically what happens, bow plane is in actually forward of even neutral, it is on quite in forward side. Normally it is forward of neutral plane, like if you go to, if you have gone to Vizag, any of you have gone to Vizag and seen this submarine, you would see that it has got a plane at the very front, but that is a very old design. Nowadays many of these planes are on the sail. See, this is called a sail, and instead of bow it is to be on a sail. So, it is not that much forward, okay, it is somewhere here. So, the difference is that this is slightly back, but the question is that CP is normally aft of this. For it to actually go forward of that, it will have to go at such a speed which is impractical. So, normally never CP goes forward of the bow plane. So, as far as bow plane is concerned, there is never reversal, okay, that is an important point. So, bow plane we do not worry, but stern plane there is a big to worry. Now, the point is which is more effective to bring it down. Now, we have seen this earlier also in a radar. See, if I have this neutral point here and radar here, the leverage I get is much more if I keep it farther off. See, if I keep it here, number one is that, see, if I had to bring it down this way, what would happen? I get a force this side, right. So, I give a moment this side, of course, I get a moment this side only if it is assuming CP is somewhere here. So, there is a, remember there is a reversal, this thing is trying to push it up, this angle is trying to push it down. So, what you may expect this go little up, no, up, then come down. So, the heave force is created here is trying to push it up Z, but the pitch moment is trying to nose down it. So, there is a reversal problem, opposite. But if you take a bow plane here, so for bow plane, number one, I am bringing it this way. Now, for bow plane, supposing I want to come down, say my bow plane is here, somewhere here, what do I do? Remember that if I do this way, then I am getting a force here and moment there. What it trying to do? They are in the same direction, both are the same direction, up and nose up, for down opposite. So, bow plane there is the hip force and pitch moment are in the same direction. So, there is no control problem as such, but in the stern plane you want to go down, but essentially you are giving an aft force, upward force. Do you see that? See here you give an upward force here, but downward moment. So, actually it goes like that, but here you give upward force and upward moment, goes like that. See there is see here I give an upward force and upward moment, so it goes like that, and here I give an upward force but downward moment, so it tries to go down eventually like that. So, this is a kind of phenomena one has to kind of wonder. Then why do you keep it aft? Because obviously for a same small angle the leverage you get is more. That same reason why radars are kept at the aft end of a ship. You get much higher leverage to kind of effectiveness to bring it down. So, normally in submarines these two planes are used for various purposes. One is to maintain depth. Sometime supposing here you want to go down without a trim, just go down like that. You can never do that with one plane, because any one plane would always necessarily produce theta and z. What you do? You have to use both the planes. This will try to nose down and this will try to make sure that you have an adequate moment up to make sure that it is in the same draft. So, that's why normally in submarines you have always two. Submarines you have got two. But look at vehicles like torpedoes, AUV, other vehicles, you do not have two. Why you do not have to? Because normally what happens, see, take AUV, there is no human sitting there. So, even if it goes down at 60 degree, you do not care, it can go down 60 degree, but in a submarine you have to control the trimming angle. You cannot go down order from 50 meter to 300 meter at 40 degree nose type, then everybody is going to fall. So, therefore, you always have to control trim, and that you do with this. Of course, there are other controller. You can design controller where you can go down at that particular trim only, that is all possible with only one also, but this is all like sort of a kind of what I should say, this the controllability issues, why the bow fins are also used simultaneously most of the time. See, now the other thing I want to tell you for a submarine is that in order for you to maintain a level drift, you want to go a straight line. You will see that you can never achieve a straight line. Suppose you have no controller, it will always either go up or go down. Why? Of course, obviously one can tell there is no symmetry here, so there is an asymmetric moment that comes. Normally it is designed to go up. So, what you should do to maintain level depth? This is called neutral angle. What you have to do? Tell me. You have to make sure that there is a small theta and small stern plane angle delta s. It turns out there is this combination necessary to maintain level depth, a stern plane angle and a corresponding trim angle. That means it cannot go straight line, it has to go with a small, maybe half a degree trim angle with a small stern plane angle. This is my zero setting. That means my zero setting is not exactly 0, unlike in a ship. In a ship my radar is at 0. So, suppose I am in a calm water, there is no disturbance, my radar is 0, I am going on a straight line. But for a submarine, if I want to go on a straight depth, you can actually think it upside down, like as if in a deep water going in the other direction. I want to maintain depth, I want to go this water line and I want to go exactly this depth. I cannot achieve that without setting a small trim angle and a small stern plane angle. That means there is a combination of theta delta is necessary to ensure that I have no m moment, no z force. That is what I am looking at. No, there should be no turning moment, no z force. And in order to get this 0, it turns out I have a setting of delta theta s, and this is what is known as neutral angle setting. neutral plane setting, and this again if you plot will turn out to be something like this, typically a neutral plane setting. Theta, as you go to speed, this speed, it goes like that, and maybe small, these are very small angle, or rather maybe say delta may go like that, because depending on the way you tell. See, if you take this to be positive theta, then positive 1 gives you negative theta, like that. What I mean is that, see here, if this is my turning this side is positive theta. Now if I turn this turn plane, no, this is negative, this is positive. So for nose up is positive, I have to, rather nose down, if I want to nose down for negative theta, I need to give positive delta s. Delta s is this one, the positive delta s. So what I mean is that if this is delta s, rather we call it theta. Now the problem is here, that reversal I said, at this point it goes to singularity and then there is a reversal there. Actually at this point, no, I think I should draw another diagram to do this. This is, I just want to show you this. Say theta delta s. So let's look at theta. Theta will look like that, let's say, and delta s may look. Which means, what it means? It means I must have this much of delta s and this much of theta to maintain, something like that, okay, to maintain level height. Now at this speed, suddenly it changes to opposite direction. What is that? This speed, this is that critical speed, the speed where the reversal happens. At this point things becomes actually singular type, very large radar angle you need to do that. So this point, this point is what is called, this is my critical speed. Okay, anyhow, so I will just close it, eventually, I mean on the submarine part. So what I wanted to mention is certain typicalities of this behavior, that in a submerged body hydrodynamics, the reason why this happens, this reversal etc. happens, if can you guess why it should happen, this reversal or this, what is extra here in this plane compared to in a horizontal plane maneuver? Horizontal plane maneuver, there is nothing like a radar angle. If I turn on the opposite side, a stable ship, it will go in the opposite direction. See, it's not that at 10 knots it goes, if I give starboard rudder, it goes starboard, and at 2 knots it goes port. It will never happen. But in a submarine we are finding for stern plane it is happening. Remember, radar is like a stern plane at the aft end of the hull. What is the difference? The main difference is, you should notice, there is an existence of the hydrostatic force. Oh, you are going to ask me, there should be hydrostatic force in ship also. Okay, what is the answer? Of course it is not in radar, because in this plane where you are doing, there is no hydrostatic restoring force. But here in this plane you have an hydrostatic restoring force. So it's a question of competition between hydrostatic force and the dynamic force. Hydrostatic force does not depend on speed, it remains same. Dynamic force depends on speed. So usually dynamic force is much more important than hydrostatic force when it goes on a speed. At a very low speed, hydrostatic force dominates, and that is where the reversal happens. Okay, so in a submarine you want dynamics to be dominant, not hydrostatics, because after all it is, like CGCV is not much also. So anyhow, with that I am ending, and so this is where we are formally ending the course. Okay, so I don't have time, otherwise we would say that what we covered in maneuvering, of course, is that basic equation, stability part, then we talked about definite maneuvers, we talked about how to determine the derivatives by experiments, and then we talked about theoretically how we can, and also radar, little bit of radar. So with that, more or less, is just a small part of maneuvering. I mean, with that we are going to close this course here. Okay.
you.